Welcome to Math GPT. Today, we're going to explore energy and momentum in electromagnetic waves, a fascinating topic in electromagnetism that helps us understand how light and other electromagnetic waves carry energy and momentum through space. Let's start by recalling what an electromagnetic wave is. An electromagnetic wave consists of oscillating electric and magnetic fields that propagate through space, even in vacuum. The electric field and magnetic field oscillate perpendicular to each other and perpendicular to the direction of wave propagation. This is what we call a transverse wave, and it travels at the speed of light, c. Now, let's talk about the energy carried by electromagnetic waves. The energy flow rate, or power per unit area, in an electromagnetic wave is described by the Poynting vector, denoted as S vector. The Poynting vector is defined as the cross product of the electric field vector and the magnetic field vector, divided by mu0, the permeability of free space. The direction of the Poynting vector is the direction in which the wave and its energy propagate. Since E and B are perpendicular to each other in an electromagnetic wave, the Poynting vector is perpendicular to both, pointing along the direction of wave propagation. The magnitude of the time-averaged Poynting vector is called the intensity of the wave, denoted by I. For a sinusoidal wave, we can express this intensity in several equivalent forms. First, the intensity equals the maximum electric field times the maximum magnetic field, divided by 2 times mu0. Since the maximum magnetic field equals the maximum electric field divided by c, we can also write that the intensity equals the maximum electric field squared divided by 2 times mu0 times c. These can be further expressed using the relation between mu0, epsilon naught, and c. So we can write that the intensity equals 1/2 times the square root of epsilon naught over mu0 times the maximum electric field squared. Or more simply, 1/2 times epsilon naught times c times the maximum electric field squared. Electromagnetic waves don't just carry energy, they also carry momentum. This is a profound consequence of Maxwell's equations and special relativity. When an electromagnetic wave strikes a surface, it exerts a force called radiation pressure. The radiation pressure depends on whether the surface absorbs or reflects the wave. Let's look at how we calculate this radiation pressure. For a surface that is perpendicular to the wave propagation direction and totally absorbing, the radiation pressure equals the intensity divided by c, the speed of light. If the surface is a perfect reflector, the radiation pressure is doubled, equaling 2 times the intensity divided by c. This makes sense because in reflection, the momentum change is twice as much as in absorption. We can also calculate the flow rate of electromagnetic momentum. The rate of change of momentum delivered by the wave per unit area is given by the Poynting vector divided by c, which equals the electric field times the magnetic field, divided by mu0 times c. This tells us how much momentum per second per square meter is carried by the electromagnetic wave. It's a way to quantify the momentum density flux of the wave. Let's look at a practical example to understand the concept of radiation pressure. The sun emits electromagnetic radiation with an intensity of approximately 1,360 watts per square meter at Earth's distance. This is called the solar constant. If we assume that an object in space absorbs all this radiation, let's calculate the radiation pressure exerted on it. Using our formula, P equals I divided by C, we get P equals 1,360 watts per square meter divided by 3 times 10 to the 8 meters per second. This gives us about 4.5 times 10 to the negative 6 newtons per square meter. This might seem small, but it adds up over large surfaces and long time periods. This is why solar sails work as a propulsion method for spacecraft. To summarize what we've learned about energy and momentum in electromagnetic waves. 1. The Poynting vector S describes the energy flow rate in an electromagnetic wave. It points in the direction of wave propagation and is perpendicular to both the electric and magnetic fields. 2. The intensity of an electromagnetic wave is the time-averaged magnitude of the Poynting vector and can be expressed in terms of the maximum electric field. 3. Electromagnetic waves carry momentum, exerting radiation pressure when they strike a surface. This pressure is twice as large for perfectly reflecting surfaces compared to totally absorbing ones. 4. The flow rate of electromagnetic momentum is given by the Poynting vector divided by the speed of light. These principles have important applications in astronomy, communications, solar sail propulsion, and even in calculating the tiny radiation pressure from everyday light sources. Understanding how electromagnetic waves carry energy and momentum helps us appreciate many natural and technological phenomena, from why sunlight warms the earth to how radio antennas work. These concepts continue to be crucial in emerging technologies like optical tweezers, laser propulsion, and quantum optics. Thank you for watching this MathGPT video on energy and momentum in electromagnetic waves.